What happens if a star explodes near the Earth? The closest star to us is the Sun. As we know, it is too small for such a finale. Instead of an explosion, it will turn into a red giant, and then into a white dwarf. But let's imagine that the mass of the Sun would be at least 8 times more. In this case, it would have ended its life with a grandiose supernova explosion. To understand the scale, the light from a nuclear bomb detonated right next to an observer is still billions of times weaker than the glow of a supernova visible from the distance at which the Sun is located from us. Supernovae are one of the most destructive phenomena in the universe. When they flare up even in distant galaxies, their light can outshine the radiance of hundreds of billions of stars, and it seems as if a new dazzling dot has appeared from scratch in the sky. This was the case, for example, on October 8, 1604, when Johannes Kepler noticed a star in the sky that had not been there before. It shone brighter than all the neighboring stars and was almost as bright as Jupiter. Her light was enough for objects to cast shadows even at night. Kepler observed this new star and wrote a book about it, De Stella Nova. He believed that he witnessed the birth of the luminary, but in fact he watched his death. Over the course of a year and a half, the radiance gradually faded and disappeared. Today we know that it was a supernova. For most of its life, the star remains in balance. Inside the core, light elements turn into heavier ones, and part of the mass is converted into energy during these reactions. It is the radiation and pressure of photons that prevent gravity from bringing the star to a point. While thermonuclear fusion is actively underway in the center, the temperature and pressure are maintained at the proper level, and the star remains stable. But sooner or later the fuel runs out. Our Sun has lived for about 5 billion years out of the last 10. However, more massive stars burn out much faster. The luminary, 20 times heavier than the Sun, will exhaust itself in just 10 million years. When the hydrogen in the core runs out, the pressure drops, the star contracts, the temperature rises, and the synthesis of helium into carbon begins. This stage lasts only 1 million years. Then, as the helium is depleted, shorter and shorter Lagrange phases are triggered. Carbon turns into neon in 1,000 years, neon into oxygen in a few years, oxygen into silicon in months. Finally, at a temperature of 2.5 billion degrees, silicon gives iron. An iron heart with a diameter of several thousand kilometers is forming in the center. Everything stops at iron. Its nuclei are so stable that neither synthesis nor decay provide energy. The iron core grows, and when its mass reaches the Chandrasekhar limit, about 1.4 times the mass of the Sun, gravity takes over. The electrons in the nucleus contract, combining with protons and forming neutrons. In an instant, the core collapses, shrinking from thousands of kilometers to a 30-kilometer ball of neutrons. This is how a neutron star is born. All the matter around the core rushes inwards at a speed of 1/4 of the speed of light, collides with the dense neutron core and bounces off, creating a shock wave. But that's not enough to cause an explosion. The main role is played by particles that usually interact almost in no way with matter, neutrinos. At the moment of collapse, a huge number of neutrinos are born, about 10 particles. They usually easily pass through matter, but many of them linger in the superdense core, transferring energy to the surrounding matter. It is this neutrino pressure that causes the real explosion. Only hundredths of a percent is accounted for by the light we see. About 1% is accounted for by the kinetic energy of the flying matter. The rest 99% is the neutrino energy. Nevertheless, even this tiny percentage of light is enough for a supernova explosion to temporarily outshine an entire galaxy. By the way, it is the neutrinos that we can register first. They burst out a few hours before the shock wave reaches the surface of the star. Not all massive stars explode in the same way. Sometimes the core collapses immediately into a black hole, and there is no bright flash. Sometimes white dwarfs that have gained critical mass due to a companion star explode. Such a supernova was observed by Kepler. After the explosion, the substance explodes, forming nebulae. This is how the Crab Nebula appeared, which remained after the outbreak of 1054. In 1,000 years, it has grown to a size of 11 light-years. So, how close does a supernova have to be for this to be a problem? Less than 30 light-years away is the destruction of the ozone layer and the threat of mass extinction. Less than 1 light-year, the atmosphere can simply be blown away by a shock wave. Up to 150 C, the danger of gamma radiation and cosmic rays. Scientists have found evidence that a supernova actually exploded nearby about 2.5 million years ago. Radioactive iron-60 has been found in the sedimentary rocks of the Earth, which can only form as a result of such events. Perhaps it was then that some of the marine fauna died. In addition, we live in a region of the galaxy with a reduced density of matter, the so-called local bubble, probably the result of the explosion of several supernovae that cleared the space around the solar system. Even more dangerous phenomena are gamma-ray bursts. Supernovae are not the limit. Sometimes the collapse of particularly massive stars, more than 30 times the mass of the Sun, leads to the appearance of hypernovae and gamma-ray bursts. All the energy is directed by a narrow beam of radiation. If such a beam were directed at Earth from a distance of up to 6,000 light-years, the ozone layer would be destroyed, and life on the surface would be destroyed. There is a hypothesis that it was the gamma-ray burst that caused the mass extinction at the end of the Ordovician 440 million years ago. It turns out that a nearby supernova explosion or a gamma-ray burst would be a disaster for Earth. But it was precisely such events in the past that made our existence possible. The shock wave of an ancient supernova triggered the formation of the solar system, and the heavy elements that make up the Earth and ourselves were formed as a result of such explosions. We can say that life on our planet owes its appearance to the death of the stars. What do you think about this story? Write in the comments. And don't forget to like and subscribe to the channels so you don't miss any amazing new stories. See you.